Well, this is it. These are the last two videos that we'll have on Organic Chemistry 2 topics. We'll cover in the first video here formation of CH bonds or CC bonds in place of CO bonds that are going to be reduced. So we're going to take and either make CH bonds from CC pi bonds, or we'll make CC or CH bonds from having started with CO bonds. So in general, when you add hydrogens or maybe take away oxygens, you're reducing a structure. Let me say that again. When you're adding hydrogens or taking away an oxygen, in general, you're reducing a structure. In the second video, we'll talk about adding oxygens back in. That's going to be, of course, naturally oxidation. But as we close with these last two videos where we're not going to make much discussion of mechanisms, I wanted to do a quick review of everywhere we've been, starting with Organic Chemistry 1 reactions or topics. And we started with, in this discussion of organic chemistry at the very beginning, we started with bond line structures or Lewis structures and how we needed to know the hybridization and partial charges of atoms within those structures. And that forced us to go into concepts like resonance to understand how pi electron density might be shifted within a structure. This was sort of our core. We needed to know it well. And then once we learned those topics of hybridization, resonance, which protons in a structure are most acidic, which sites or nitrogens, oxygens, carbons would be most basic within a structure. Once we delved into those topics, we took off into naming, stereochemistry, reactions of RXs with nucleophiles, where we saw strong bases typically give SN2 or E2. Weak bases can be somewhere in between. They can give a lot of different products depending upon the solvent and conditions. Non-bases are things like just ethanol and water tended to give E1 and SN1. And then we moved from RXs to alkenes, alkynes, and dienes, and how they can react with electrophiles, things that are electron poor. And their pi electrons could come out and attack as nucleophilic sites. And we also looked at alcohols and starting into ethers in Organic Chemistry 2, looking at how alcohols, once protonated, gives us a leaving group that we can replace the water with a nucleophile and have that bonded to the R. So we had acids like HBr, where bromide could replace water. Ethers could also react with HBr, where the ether was protonated just like an alcohol to give us, instead of water as a leaving group, it would give us an alcohol as a leaving group, and we could attack the R here with a halogen or a weak base. And then we had epoxides, and how we discussed how they can be reactive in both acids and base conditions because of the ring strain, and how we can have substitution at these carbons of this oxygen. Then we moved into kind of the latter half of Organic Chemistry 2, benzene rings, and how they can attack an electrophile, much like we saw with alkenes, alkynes, and dienes. But we had to reestablish aromaticity, so we didn't have addition reactions, we had substitution reactions, electrophilic aromatic substitution. Then we had the opposite of that, where the ring was attacked by a nucleophile, so nucleophilic aromatic substitution. Then we slipped into talking about carbonyl chemistry, how we could have carbonyl chemistry starting with either class 1 carbonyl, where we have a leaving group, and this nucleophile can substitute it. Or if we have no leaving group off the carbonyl, we can have addition products, or have addition products that go on to react to kick off this oxygen in an elimination of water. Then lastly, as we closed in the discussion of carbonyls, we looked at all the chemistry that can be done when we start off not with a nucleophile attacking as a nucleophile, acyl substitution or acyl addition, but if the nucleophile acted as a base. If it acted as a base towards an alpha proton, alpha carbon that has an alpha proton, we can do a lot of the chemistry with a new nucleophile using old acyl substitution reaction mechanisms or lines of reaction. We can use a new nucleophile to run acyl substitution, Claisen condensation, or we can use that new nucleophile, that enolate, to make enones and aldols. That's sort of more the attack of class 2 carbonyls. So a lot could be done through extraction of the alpha proton. Now I don't have it up here, but we're going to now end with reduction and oxidation. And I'll spend more time on this latter one. We'll find that a lot of reactions we've already seen for reduction reactions. That is, again, formation of CH bonds or abstraction or removal, I should say, of oxygen. So to remove oxygen from a structure and replace it with carbons or hydrogens, you're reducing. So let's look at those reduction reactions that we've already seen in the past from OChem 1. So we're going to head into reactions we've seen already in hydrogenation of alkenes and alkynes, partial reductions of alkynes, and also dissolving metal reductions, which is also a partial reduction, and we'll review hydrides, and we'll stop there. The video will not cover, though we have seen, the Wittig reactions, wherein we use the triphenyl phosphonium ylides, whatever R is, and we can take and replace that oxygen with that R group, and we get a removal of oxygen through the formation of a phosphorus-oxygen bond. We remove the oxygen from this carbon and replace it with a carbon. That is a reduction reaction. We will not have that one in this video, but that is a reduction reaction. Alright, so let's look at those reactions we have seen from OChem 1, our videos way back in Organic Chemistry 1. We looked at how a carbon-carbon pi bond could be converted to a carbon-carbon hydrogen bond. Sorry, carbon-hydrogen sigma bond. So we could take the pi bond and break it, the pi bond, keep the sigma, and have these CH bonds that are new. We could do that by using metal catalyzed hydrogenation, and I've left X and Y undefined. We can think of that as our CC double bond, and that would go to then a CC single bond, where we've taken the pi bond away. Using a metal catalyst, we've inserted that hydrogen into this pi bond, so we have two new sigma bonds in place of the old pi bond. This is a reaction, though, that can be done beyond just carbon-carbon double bonds. We've seen it done with carbon-carbon triple bonds, where we can take two pi bonds away and add in a total of 4 hydrogens. But we can also do it, that's why I left it undefined, X and Y, we can do it with carbon and nitrogen triple bonds. We can reduce both sides so that this gains 2 hydrogens and this gains 2 hydrogens. We can do it with an imine linkage, where we can take and add across this pi bond a hydrogen here and a hydrogen here, and we can do it across a carbonyl, adding a hydrogen here and a hydrogen here. Now, in general, it gets a little bit harder to do it on this side of the, I guess, list of pi bonding here compared to carbon-carbon or carbon-nitrogen pi bonding. It tends to be more polar, can be harder for it to get to the metal in general. So in general, it's an easier thing to reduce an imine than a carbonyl in general. Now the mechanism for this is pretty straightforward, and I'm not going to give much attention to this, but we just have a metal surface that our carbons here in black have to bind to. So the pi bond actually breaks as it makes, I guess, contact with the metal, and hydrogen that's already pacified or absorbed onto the surface of the metal starts to move in. So we see one sort of sliding in from the left here, and another one can slide in from the right. And in the end, these being hydrogens are bonded to the same side of the carbon-carbon sigma bond. So we say that's a syn addition of those 2 hydrogens, syn addition. We see that with metal catalyzed hydrogenation, is that it's a syn addition. So again, don't forget, we can do more than just reduce carbon-carbon double bonds. We can reduce carbon-carbon triple bonds, carbon-nitrogen triple bonds, carbon-nitrogen double bonds, and carbon-oxygen double bonds, so that we end up taking all pi bonds away and replacing them with hydrogens. Now, one interesting facet about this reaction is that we can take metal catalyzed reduction conditions, metal catalyzed reduction conditions, are hydrogen gas and metals being either platinum, palladium, or nickel. We can also take nitro groups, NO2, down to amines. That's a different sort of reaction because we're taking and breaking sigma bonds. We can use, usually nickel and hydrogen can be used to take this down to amines, nitro to amines. We can also do it with azides. We can take azides, N3, down to ammonia as a group off of some substrate. So we can take N3 and change it to an NH2 group. Nitro groups and azides, N3, can be fully reduced to form NH2 groups through metal catalyzed hydrogenation. And lastly, one reaction that has not been presented is that we can also use lithium aluminum hydride. Now this is a different type of reagent. This is a polar reagent. This is using the nonpolar hydrogen. Lithium aluminum hydride is able to reduce amides to form amines. So I just wanted to throw that in also since we're talking about formation of amines. We can take lithium aluminum hydride and work it up with water, and in the end we'll get a complete removal of the oxygen in the carbonyl and replacement of that with hydrogen. It has to do with the interaction of the aluminum with the oxygen, and that comes off as aluminum oxide, but in the end we get just an amine left. Now we have seen already partial reductions of alkynes to alkenes, so we can do that in two different ways. We could add the Lindner catalyst, which was just sort of a polluted metal catalyst that doesn't allow for the alkene to go on to reduce to an alkane. So we could stop short of an alkane and stop at just an alkene, having only added 2 hydrogens across one pi bond. We could also do that though in a trans manner using lithium metal and ammonia. Now this is what's called a dissolving metal reduction. So I put it in yellow here. It's different in its mechanism than what we saw on the last slide, metal catalyzed hydrogenation. This is called a dissolving metal reduction. In the end, lithium gives the electron and ammonia gives the proton, but you get in the end still a very active form, we might say, of the hydrogen, a reducing form, this hydrogen with its electron. He gives the proton, he gives the electron, and we get a reducing form of hydrogen, and we get a trans addition across the pi bond. We're breaking just one pi bond with lithium and ammonia to give us a trans orientation of the 2 hydrogens that are added. We can also use sodium and ammonia here. And we know, of course, we can fully reduce if we don't use a polluted form of the palladium catalyst. We can have a full reduction. 2 pi bonds, we get 4 hydrogens. So each pi bond giving us 2 hydrogens, we can have that 4 hydrogens put on because we can take 2 pi bonds away and leave just the CC sigma bond. Now I've showed them here in a trans orientation. That's only because these R groups, after we have full reduction, would want to be as far apart from each other as possible. Of course, this is still a syn addition. These came on the same side. We have seen already dissolving metal reduction as we kind of review. We have seen that in the formation of a CH2 group from a carbonyl using the Clemmensen reduction. This is also a dissolving metal reduction. This is one you need to know, the Clemmensen reduction. Clemmensen reduction. We've seen that using the same sort of conditions, a metal that provides the electron and the HCl or water that provides the proton. This is also a dissolving metal reduction wherein we take carbonyls to CH2 groups. Okay, moving right along, we've already looked at with lithium aluminum hydride how it could reduce amides to form amines. Lithium aluminum hydride can be used to take the carbonyl off, basically amides, and leave just the NH2 group behind. We've seen ketones and aldehydes react with sodium borohydride to give just a alcohol where we've added across, again, the pi bond, we've added a hydrogen, but we've done it in a different way. Here it's just a nonpolar hydrogen with a metal catalyst wherein we can take and add a hydrogen here. There's one now there. And we've added a hydrogen here. We've taken the pi bond away and added 2 hydrogens. Here we do it in a different manner. We have a polar reaction. These are then going to only act towards polar double bonds. The borohydride delivers a hydride to the partial positive, so this one really comes from the borohydride, and ethanol provides the proton that's going to be scavenged by this oxygen that has a partial negative charge. So this is a non-polar metal catalyzed hydrogenation reaction that can work with any pi bond, and again, this was in general less reactive than CN double bonds and CC double bonds. But in general, this can work with any pi bond in general. But being a polar reagent, borohydride, aluminum hydrides, we need to use a polar double bond. So CO, CN, but not CC. So alkenes, unlike imines or even carbonyls, alkenes, CC double bonds, being nonpolar, are not reduced by lithium aluminum hydride or borohydride. Just an isolated carbon-carbon double bond is nonpolar. It cannot be reduced by aluminum hydride or borohydride. We know that lithium aluminum hydride is more vigorous or reactive, so it requires a separate workup, but borohydrides, being less reactive, can be used in the presence of a protic solvent, so that this protic solvent can give the oxygen its proton after the hydride has attacked the carbon in the carbonyl. All right, we're almost done. I just needed to cover one more. We have gone through quite a few reactions looking at the reactions here. Catalytic hydrogenation, we've looked at that, how we can use a metal and hydrogen gas to reduce a wide range of carbon multiple bonds, or carbon nitrogen pi bonds, or even carbon oxygen double bonds. So we can use a lot of different pi bonding systems for catalytic hydrogenation. We've looked at partial reduction and dissolving metal reduction, hydrides and how these are polar, so we have to have a multiple bonding between CN or CO but not CC. And we're going to stop short of the Wittig reaction, but there was one other way we could take and reduce down carbonyls. We saw the Clemmensen reduction using dissolving metal reduction conditions. We also know there's the Wolff-Kishner method of reduction of carbonyls, where we can make a imine from the hydrazine and the ketone. We can make an imine that then in base conditions can be reduced down to a CH2 group, where this comes off as nitrogen gas. So we saw that also. And I do want to mention just at this point, there are conditions where we can have metal catalyzed reduction wherein the carbonyl is not reactive enough with the set metal and the hydrogen pressure, where we can go to an imine, and these in general are more easily reduced with metal catalyzed hydrogenation than CO double bonds. So you'll sometimes see what's called reductive amination reactions, where they set, I'll just go ahead and show it, they set conditions for metal catalyzed reduction. So they'll use some sort of metal and a certain pressure of hydrogen gas, and what they'll do is they'll rely on the fact that some amount of an imine is formed, and this being more reactive with the set conditions of the platinum or metal that's used, you can change the reactivity based on the metal you use, and you can change the pressure of the hydrogen gas in the system. You can work on the more reactive CN double bond so that in the end you get not a, reduction to leave an alcohol, but you get an amine. This is called the reductive amination, and there are other ways to do it, but just one that's used is to have these set as far as pressure and the metal, that it only trips or clicks, it goes into reaction when we have a CN double bond, which can be in general more reactive than the O double bond, because it's less polar, and there's some things that go into that. But this is just reductive amination that can be used, where we make an imine, and these conditions here are set just that this reduction is occurring when we have a CN pi bond and not a CO pi bond. Bye-bye.